Yeah, so there's two parts now in the next less than 1 hour. There's first me talking about this impact, and this is setting the stage for why it's important to uh, ensure the quality of post-quantum software. And then Bo-Yin will be talking more specifically about something constructive. So my part will be about things going badly, and he will give you a happier thought for the second part. All right, so jumping into my part, the impact of post-quantum bugs. The starting point here is that we have many cryptographic libraries, many cryptographic implementations for many years, and they have had many vulnerabilities. The software has exploitable problems. Now, sometimes a crypto system is broken, but even when the crypto system seems okay, the software has problems. And that's what's studied in, for example, this paper from 2021 from Blessing and Spector and Weitzner. They were going through, they picked only 8 libraries, some of the best known crypto libraries. There are many more cryptographic implementations, but they picked 8 libraries that are used in many applications. And then they looked at the CVEs. So these are vulnerability announcements. If they are registered, CVE is a particular system for tracking vulnerability announcements. Not all vulnerabilities are announced there. Some cryptographic libraries do not issue CVEs, but many of them do. And this is a common place to announce vulnerabilities. And this paper looked at vulnerabilities in these libraries between 2010 and 2020, the announcements in that range of years. And there were, I think it was 300 vulnerability announcements in these libraries. Many different things going wrong. And sometimes there were buffer overflows, sometimes there were bugs that were exploitable in different ways. And there's lots of information in this paper. It's very interesting looking at what went wrong in this cryptographic software. Let me point out 3 important lessons from the paper. So first, depending on exactly which library you look at, it's something like 1 vulnerability announcement per 1,000 lines of code, maybe per 2,500. It's maybe different numbers depending on what exactly you look at. But roughly, if there's 1,000 new lines of code in a cryptographic library, then you expect about 1 vulnerability announcement from those lines of code. All right. Next important lesson is that when there's a bug added to the software, in this paper, they looked at each of the bugs when it was fixed versus when it was added for libraries that provided that information. And they found that the average time was 5 years between introducing the bug and fixing the bug. Of course, it also takes time to patch the deployed libraries. I mean, a library is released and then it can take years before everybody has upgraded to the new version. So the actual lifetime of a bug is even longer than 5 years on average. Also, this 5 years is just the average time. Some bugs are found faster, but some bugs are found slower. And because they were only looking at known CVEs, they were only looking at bugs that have been found, but that's biased against bugs which take even longer to discover. So probably the average is even more than 5 years for all bugs. Basically, every year, about 80% of the bugs are not discovered. 20% are, but then the rest, well, they're still maybe discovered the next year, maybe the next year. It can be 10 years or more before a bug is discovered. We've sometimes seen bugs which are discovered after 20 years or longer. All right, another lesson from this paper is they looked at the different types of CVEs, and some of them they said are actually cryptographic. All of this was in crypto libraries, but some of them they said were really in the cryptography, not in, for example, a buffer overflow in X509 certificate handling. That is not really cryptographic code. It's in a cryptographic library, but they looked, a lot of the CVEs were actually in the cryptography. And about 1 out of 8 of those are severe vulnerabilities. And what does severe mean? Well, when somebody registers a vulnerability in the CVE database, they give a rating of how severe it is. And well, they say it's severe or not. OpenSSL, for example, OpenSSL policy says timing attacks are not severe. Even if you have a demo exploiting the timing attacks, OpenSSL just says, no, it's not severe. So it depends on what the libraries say, but some bugs are clearly exploitable, and they do admit sometimes that those bugs are severe. And about 1 out of 8 CVEs is severe. So, okay, looking at these numbers, if there's 1,000 lines of new code, then you expect a CVE. If there are 8,000 lines of new code, you expect an exploitable CVE. And you expect that that will still be exploitable for, well, 3 years, 5 years, 8 years after it's introduced. All right, what does this mean for post-quantum cryptography? Well, in 2017, there were many submissions to the NIST post-quantum competition. Of course, there are many papers all the time about post-quantum cryptography, but NIST had a requirement of writing software, which sometimes people do anyway, but NIST was saying everybody must provide software. And of course, users who want to use post-quantum cryptography, they need software. I was looking at this software, and one posting about this in October 2018. The deadline was end of 2017, December of 2017. And well, by 2018, I was saying that this project produced the largest regression ever in the quality of cryptographic software, the largest loss ever in the quality of cryptographic software. I mean, cryptographic software in the 90s was just terrible, but it was getting better. People were fixing things, improving the quality, and making things better and better. And well, now it's just terrible again. And what was I looking at for this? Well, I was looking at all these different pieces of new software, which first, they're new. And that means people have just been writing these, and it takes time to find the problems. And second, it's very complicated. This is more complicated than RSA software, for example. A typical post-quantum system has much more software than RSA or elliptic curves. You can make an elliptic curve implementation in much less software than a typical post-quantum system. And okay, so there's all this new complicated software, and of course it has lots of problems, and it takes time to fix these problems. Some examples of bug announcements that we've seen in post-quantum software, I've just listed some on the slide. There are more, but well, I had to fit this into the slide. So here's some examples of well-known names of cryptographic systems, post-quantum systems, where there have been bug announcements. Not necessarily exploitable, sometimes exploitable. And then there's also, I'm just focusing on bugs here, but there are also many, maybe even more announcements of timing variations. And some of those are also exploitable. But okay, let me just focus on bugs. There are more and more post-quantum bugs. And the situation is getting worse because what's happening is lots of people are writing new post-quantum software. It's not just when you build a new post-quantum system, as a designer, well, maybe you want to write software for it, or maybe somebody says you have to write software for it, and you want to show here's how to implement it. But then there are many libraries which write new software for the same systems if they want to deploy it. Why do people do this? Well, maybe they think, oh, I have a library in a different language, and so I should write the software in this other language. I want to write post-quantum software in, ooh, you used C, well, I want to use Go, or I want to use Rust, or I want to use Zig, or whichever language people like. They want to write new software in that language. And so they write, that's one of the reasons that people write new software. Or they say, well, yeah, I'm using C++, for example. I could just copy the C software. It will work in C++. But I have my style of a cryptographic library, and I don't think that your software works with that style. And so I want to have different software because, well, people just have different ways of writing software. And so you get more and more libraries. There's something like 50 post-quantum libraries already. And then, there are many general purpose libraries, many special purpose libraries that are integrating post-quantum software. And then most of those are writing the software again, writing new software, even if it's the same cryptographic system. And so you end up with, well, if you look at MLDSA, for example, I'll say more about MLDSA bugs as an example later in the talk. But a typical MLDSA implementation has thousands of lines. And if people optimize it for multiple architectures, it can be much more software. And then there are many, many libraries, and that's just MLDSA. So we're ending up with millions of lines of new post-quantum software in a lot of different libraries. And of course, 1,000 lines of code, there will be a bug. 10,000 lines of code, there will be a severe exploitable CVE. And so we will have many, many bugs exploitable. Some of the bugs will be caught by tests that people use, but many of them will get into deployment, and some of those will be exploitable. So we have a real disaster here with post-quantum software. Now, the example that I want to spend a few slides on here is dilithium, or MLDSA. Now, okay, technically, there was the original dilithium in 2017, and then there was a new modified version of dilithium, not interoperable, not compatible, in 2019. And then there was another version in 2020. And then there was a draft, there was a 2022 version. I think, okay, the numbering system is there was dilithium 1.0, 2.0, 3.0, then I think 3.1, then there was 3.2. So that's not an official name, but there was another change in dilithium for the draft MLDSA standard, and then the final MLDSA standard in 2024. So, okay, 6 versions of dilithium, if I counted correctly. 1.0, 2.0, 3.0, 3.1, 3.2, 3.4. Yeah, 6 versions. They're very similar, but there are changes. For example, some of the smaller parameters they started feeling uncomfortable with, and so they removed the smaller parameters for dilithium, moved up to bigger parameters. And there were other things that were trying to do sort of security fixes. And then there were some other things which were, well, not maybe about security, but they changed interoperability. So, okay, various versions of dilithium ending up with the final MLDSA. And of course, every change means some change to the software. So, okay, people were writing all this new software for the different versions of dilithium. And then now people are suddenly writing many more MLDSA implementations for cryptographic libraries. Now, are these all magically bug-free? Well, 1 month after the original dilithium submission to NIST, end of 2017, beginning of 2018, there was an announcement from the Crystals team about dilithium. They said, "We're grateful to Peter Pessel for notifying us of an implementation error in a randomness generator of our NIST submission." Now, this is actually a little bit confusing. When you see a randomness generator of the NIST submission, then, well, was NIST requiring dilithium software and randomness software, and then the randomness software had a bug and the dilithium software did not have the bug, and so you're okay using the dilithium software but not the randomness software? That's not the situation. NIST did say submit the software and separately submit some test code generating some randomness, but this error was in the dilithium software. Anybody using that dilithium software, it would have been a security disaster. What they said was the result of the bug was that the same randomness ended up being used for pairs of consecutive coefficients. And again, this was a bug in the dilithium software itself, not the randomness, not the random number generator. Anybody using dilithium with any RNG, plugging in any RNG into dilithium, it would have been exploitable. And then they said this reuse of randomness can easily be exploited to recover the secret key for dilithium. So the software, the dilithium software as submitted to NIST, should not be used in any real application. I'd like to look at the actual code here. There was the original code, the modified code. I'd like to look at the modified code to give you an idea of what the bug was, to give you an idea of how you could put in this mistake into the software. If you look at the corrected software, then there are two independently generated random numbers, T0 and T1. And then those are put into some array. Well, it's a little bit complicated. If T0 is less than something, then some function of T0 is put into a bracket counter plus plus. So into the next position in the array. And if T1 is less than or equal to something and the counter is not overflowing, then this function of T1 is put into the next position in the array. So that's what the corrected code looks like. Now, the first question I have when I look at code like this is, wait, what if counter equals len? What if there's a buffer overflow in the first part? Well, there was an outer loop around this, which was checking is counter less than len. And so only after the first move, after the first a bracket counter plus plus, then the code had to check again, is counter less than len. But aside from that, these two assignments into the array are very, very similar. And if you imagine writing code like this, you probably write the T1 code, and then you copy and paste those lines to get the T0 code. And then you say, oh, I don't need counter less than len. So where there's, I don't know if this is visible on the screen, but no, I guess not. Give me a second. Click a button here. Yeah, so there's a spot on the screen here where I'm sort of waving the mouse and I guess messing things up. At that spot, there could be for T0 checking is counter less than len. And well, then somebody copying and pasting would delete that code, thinking it's not necessary. And then they have to remember also change T1 to T0 at two spots. So taking the third and fourth lines, copying and pasting, getting the first two lines, and then remove counter less than len, change T1 to T0, change T1 to T0 again. But now, if you imagine, oops, somebody misses one of those changes or just forgets to change T1 to T0, then they're putting T1 into the array twice. And so instead of two independent numbers, random numbers in the array, it's just copies of one number in the array. And also, this bug passes normal tests. It passes interoperability tests. It even passed the known answer tests that Dilithium was using because all of their implementations were having the same bug and producing the same wrong known answer tests. So this sort of bug, it's easy to make this mistake. It's easy for this to pass tests. And actually, there's more ways to make the same mistake. They actually made the mistake in a different way. The original code did not have T0 and T1. The original code had one variable T, and what they were thinking was generate T, put it into the array. Generate another T, put it into the array. And that's four pieces of code. Make a random T, which is a little complicated. Use that T, put it into the array if it's small enough. Make another random T, put that into the array. But they got the order wrong between the second part and the third part. They generated a random T, then they generated T randomly again. Oops, forgot the first one. And then they used it twice. And there's more ways that you can make the same mistake. It's a really easy mistake to make. And well, they made this. And this is just a few lines inside many, many lines of software for Dilithium. Now, because there are different versions of Dilithium, they never demonstrated the exploit that they said was possible. And also there are changes to Dilithium, 6 different versions. And so you might wonder, okay, is it actually exploitable, or was it just exploitable for the original Dilithium, maybe not for current MLDSA? Maybe if people say that MLDSA is magically bug-free, maybe they mean that MLDSA has some protections against this. No, MLDSA has the same problems. There are many, many lines of code in MLDSA where you can make these mistakes, and including these lines. And so I implemented MLDSA and oops, put in the same bug. And then I wrote a demo to exploit that. Now, the original announcement said they can recover the secret key. I don't think they know how to do that. I don't know how to do that. I do know how to recover, well, part of the secret key, which I say is equivalent because that part is good enough to generate signatures. You don't need the rest of the secret key to generate signatures. It's just a little bit slower to generate signatures using this equivalent secret key. So, okay, my script takes a public key, takes two signatures, and then with very high probability, you can try it experimentally. With very high probability, it computes an equivalent secret key, and it takes less than 1 second to run on one CPU core. And this is a script in a high-level language. If you rewrite it in C, I think it'll be less than 1 millisecond to compute an equivalent secret key. And then, well, okay, I'm claiming it's equivalent. Is it actually equivalent? Can you actually forge signatures? Sometimes the dilithium team has said things like, oh, yeah, there's a leak of information, but that's not exploitable because blah, 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 blah. So, okay, my script also forges signatures. It uses this part of the secret key after figuring out this part of the secret key, starting from, again, a public key and two signatures from the software with one little bug. It finds part of the secret key, an equivalent secret key, and then it checks, yes, I can forge signatures. And those signatures pass verification. And I posted a paper which includes explaining what's going on here and also another demo for another bug and then more stuff in the paper. So everybody can download this demo script and verify everything that I'm saying. Okay. What's the bigger picture of how much do we expect to go wrong in MLDSA? Well, here's the normal software engineering way to think about this. If you look at MLDSA implementations, then again, it's thousands of lines per library. Each cryptographic library adding MLDSA software, thousands of lines of code, maybe more depending how many optimized versions they have. Maybe they have portable code, Intel code, ARM code, and the number of lines of code just keeps getting bigger and bigger. And I mean, even a Python implementation is something close to 1,000 lines of code and not suitable for deployment. So it's a complicated crypto system. And then, all right, how many bugs do we expect? Well, maybe this code is better than average cryptographic code. Maybe it's only out of 2,000 to 4,000 lines, maybe it's only 2 vulnerabilities, not 4 vulnerabilities per library. And about 1 out of 8 of those will be severe. At least that's what we expect historically. And I mean, we don't know until we see many vulnerabilities. We don't know how many of them are going to be exploitable, what the exploitability rate will be. We did see the original dilithium bug was exploitable. Now there are more MLDSA bugs that have been announced, and well, some of those are exploitable, some of them are not. But okay, the estimate is 2,000 to 4,000 lines per library, about 2 vulnerabilities on average, maybe more, maybe less. And then 1/8, so one vulnerability out of 4 libraries should be exploitable. That's at least estimate based on 1/8 of cryptographic vulnerabilities are exploitable. And this is something, there are so many libraries that this is not a process of just, is the community going to have one piece of software that it's going to get that right? Hopefully, there are many, many libraries. Some of them will have exploitable vulnerabilities in MLDSA. All right. When are the bugs going to be fixed? Well, roughly, except for the original dilithium software, basically all of the MLDSA libraries are new last year or this year. Let's say it's half of the libraries were last year, half of the libraries this year, adding MLDSA software. And maybe some will add it next year, the year after, but okay, let's just assume last year and this year. And then about 20% of the bugs are found each year. So the bug rate slowly decreases each year. All right, how much damage will this do? Well, some fraction of keys will be coming from these vulnerable libraries. And then there are maybe 2 to the 30 total MLDSA signature keys, depending on how much it ends up being used. But there's a lot of signature keys in many different applications. And then maybe the attacker does not have enough CPU time to break all of the exploitable vulnerabilities, so you can estimate the effect of that. And then, well, if you take a look at my paper, then it includes doing these calculations and coming up with a graph of the number of broken MLDSA keys, depending on, is it a small scale attacker or a large scale attacker, different computational resource assumptions. Also, in the same graph, I'm covering what happens to elliptic curves, or what happens if you sign with both elliptic curves and MLDSA. And then you get some different graphs. And also, so looking at the bug rate for elliptic curve software, looking at the effect of quantum computers. For many years, I've been estimating that public quantum attacks will be here around 2032. That's my median estimate. Secret quantum attacks should be earlier. It's hard to figure out exactly how far ahead the attackers are. But I think that, for example, the Chinese government is likely to have a quantum computer that's capable of breaking some elliptic curve keys around 2029. And this is something, that estimate, I gave that estimate publicly years ago, many years ago. And this is something where the technology has been evolving consistently with what I've been estimating. There are some other people who think, oh, everything's changing very quickly and our estimates have to be revised. I think that's because people have not been paying attention to the evolution of quantum technology. Anyway, so I expect that elliptic curve attacks will start sometime around 2029, maybe later, maybe sooner, and we won't know. What we'll see is public attacks a few years later. But then those won't break every elliptic curve key because it's very expensive. It'll be the first quantum computers will cost maybe $1 billion, and they'll break thousands of elliptic curve keys per year, which is not billion keys. There are many elliptic curve keys being used. And so, okay, as quantum computers get cheaper, then the number of elliptic curve keys being broken will increase. But it will take quite a few years before elliptic curves are useless. For the near future, elliptic curves are much safer than MLDSA. And well, using both, if you sign with both, then, well, you have to look carefully because there might be issues with the integration, but it stays safer than MLDSA for many years. So that's clearly the right thing to do. Okay, I have one more slide here, and then I'll turn things over to Bo-Yin to give you a happier picture of what can be done. But just to give you one slide of general recommendations of things that you can do. First of all, first step towards trying to recover is to admit that there's a problem. This is in the United States, there's these organizations like Alcoholics Anonymous, where people who are addicted to alcohol, they go and try to recover. And the first step is to admit they have a problem and they need to do something about it. So, okay, that's step one. And I mean, already a lot of people have trouble with this, even when you see many, many bugs, many exploitable vulnerabilities. There will still be people who think, ooh, this is, no, there's no problem, or there's no problem for me, but there is a problem. All right, next thing, again, do elliptic curves plus post-quantum software. So if something is broken in the post-quantum software, then, well, hopefully the attacker is still having trouble breaking the elliptic curve part. It's really low cost to do elliptic curves on top of whatever post-quantum system. We already have the elliptic curve signatures, elliptic curve encryption. So of course, just keep that and also do the whichever post-quantum system. Don't do solo post-quantum software. Make sure when you're writing your C software, do a double check of writing your specification in a high-level language like Python or Sage, which, I mean, for MLDSA, for example, it's still many hundreds of lines in Python or Sage to implement MLDSA, but it's still much simpler than the C software. And somebody writing it in Python is probably not going to make the same mistakes as somebody writing it in C. And then test that the Python code and the C code are producing exactly the same results when they're given the same randomness. And then that gives you a chance of finding bugs. Sometimes there can be bugs which get past this, but this is a very, very useful test to do, is making sure you're writing Python software for your specifications and then use Python to test. Another very useful way to catch problems in C software is using memory safety tools. And the baseline for this, there are many possible tools, but sort of the default thing that you should always do is using Valgrind and Address Sanitizer. Address Sanitizer it knows about the C language and it's sort of integrated into C. This is where you do GCC minus F sanitize equals address. And so Address Sanitizer will look for, are you overflowing arrays? Valgrind is more compatible with assembly, for example. It does not care about what compiler you're using. Valgrind works on binaries. It has some disadvantages compared to ASAN, so use both of those, and these will catch many problems with C code. All right, another thing you can do in SuperCop, there are many tests built in. Now, all you have to do to make this work is match the SuperCop interface. For example, for KEMs, there's 3 functions that you have to implement. And well, lots of people have been copying this interface, so most of us are using it already anyway. And then actually plug it into SuperCop. And SuperCop's tests include Valgrind and many more tests. And it'll, for example, include timing leaks, which is using Valgrind in a different way. Okay, and last thing on my list is often you can catch problems with formal verification. Now, I'm saying try because if this is used systematically, it will catch all bugs. But that's very expensive to do systematically, but you can often do it on at least some subroutines and try seeing if you can do it for the entire software, but at least start by trying some subroutines. And so these verification tools, for example, CryptoLine. Now this integrates 2 types of verification. This is something you compile your software and then CryptoLine will look at your binary, convert it into CryptoLine format. And then what you have to do is introduce some assertions about what you expect is true about that software. And CryptoLine will verify those assertions. And there's 2 important things that it will combine as testing tools for these assertions. One is SMT solvers, which can check, is it possible to violate the range that you expect for variables? Can you have an overflow, for example? And these SMT solvers, it's not just testing individual inputs. The SMT solvers will test, is it at all possible for any input to violate these ranges? Plus, CryptoLine uses computer algebra systems to check algebraic facts. For example, polynomial arithmetic or working with big integers. Maybe you have some big number arithmetic for sampling for a CDT, for example, and you need to check, are you doing the big number operations using small arithmetic operations? Are you doing that correctly? And well, CryptoLine includes algebraic verification. And so you put in assertions and CryptoLine will check those for you. All right, another example of these verification tools, S2N Bignum. This one is saying, all right, you have some software, again, written in, say, assembly. It doesn't really care how the software is generated. And then it uses a general purpose proof system called whole light and says, can we verify in whole light, generate a proof that the software works correctly? And this is very powerful. And for the Bignum software in S2N Bignum, there are complete proofs for that software working correctly. But, well, it does take work to do that for complete software. Safe rewrite, this is the opposite direction of it. It's very automatic, but it only works for little pieces of software, very small subroutines. For example, you might have a subroutine of splitting something into high bits and low bits, doing a little bit of arithmetic, computing the maximum of some numbers in constant time. And those things, safe rewrite will check automatically using SMT solvers that versus reference software, make sure that always works correctly. And the good thing about it, it's only for small subroutines, but it works completely automatically. It's very easy to plug things into that. And then if it says yes, then you're done with no extra work. And then there's also specific tools for specific types of subroutines like SortVerif, which is for verifying sorting software. You have to be careful here because it's very difficult to get to everything being formally verified. And sometimes people will exaggerate how much they verified. I have a link here to a paper which is finding some bugs in some formally verified software. But it is very useful to verify what you can. So that's my recommendations. And then for the rest of the time, I will turn things over to Bo-Yin.
Okay, so uh, like there is always a useless slide about post-quantum cryptography, but basically we are trying to do secure and fast implementations of PQC standards. And KpqC is one of those which are candidates for standardization or has become standards. And most of the KpqC KEM stuff is doing number theoretic transforms. And this can be complicated. And part of our work is trying to very formally verify that at least the key parts are correct. So there are two KEMs in KpqC. There's N2 plus and SMAUC-T. Sorry if I misspelled anything. And the main thing for N2 plus is that it's a variation on the NTT true of 2019, except that it's not on the field of 7681, it's rather on the field of 3457. The smaller number makes it slightly more secure. And the idea is that there is an omega and omega to the fifth split. And after that, we will do an incomplete entity to x to the 4 minus omega, as opposed to x cubed minus omega in entity true. And also the need for lifting if you use standard and true. In SMAUC-T, we have a module LWR where it's very similar to Saber. In Saber, it's the ring of modulo 8192, and in SMAUC-T, it's 1024 or 2048. In both cases, you cannot have native entity because, well, I mean, 2 to the 10 and 2 to the 11 and 2 to the 13 are not rings in which you have principal roots of unity that we need. And we will give a very quick overview of what's going on. The standard FFT is a specific Chinese remainder theorem in the ring of Rx. As long as 2C is invertible, we can split x to the 2n minus c squared into x to the n minus c and x to the n plus c. And the mapping is very simple. And it corresponds to what's called the Kurituki butterfly and the gentleman sand butterfly. And these are basically available because we have this particular relation. And so there is a multiple of x to the n minus c and one of xn plus c that is exactly 1. So we can compute this simply and quick and without any concern that anything will go wrong. And so this will take like n adds, n subs, and n multiplications. And what this means is that we have a n log n like algorithm. And a long multiplication is equal to 2 half-length multiplications in the right, and that's what gives the n log n. So in FFT and NTT, as long as we have the correct principal root, and we can split things repeatedly. So we split it once, twice, and the thing is, it comes out exactly, if you just keep splitting, it just comes out evaluations of at principal roots that's in bit reversed order. Sorry, not principal roots, roots of unity in bit reversed order. So what happens is that you can see how the numbers are, and it turns out that it's exactly when you are done, the roots are in bit reverse order. So if there are 8 roots, the order is 0, 4, 2, 6, 1, 5, 3, 7. And that's just a very common situation. And the thing is, when we are doing FFTs, we often rearrange the output. We are doing NTTs for polynomial multiplication. And in any of those software, if you look at it, it never reverses the order of input-output because we don't need to do that. We are not doing spectral analysis. And for SMOG, we have negacyclic entities, and this is like a rearrangement of principal roots of 2 to the k+1. And the thing is, it's almost exactly as if it's the same thing as the normal entity, except that like you only have the upper half of the transform. So this is a classical case of like splitting a polynomial into 16 coefficients. And the thing is, it's a gradual process, and you can stop any time. And if you stop somewhere in the middle, this is called incomplete entities. A name that I actually coined myself. And this is, if you look at Kyber, in the beginning, most people have trouble understanding what's going on in the Kyber entity. But it's really a half-finished MTT if you look at it. So the thing about FFTs is that sometimes you change the polynomial modulus. If you are doing n true, then you need to change the polynomial modulus. And in SMOG T, we don't need to do that because the original form is a cyclotomic polynomial. The other thing is that we need to change the coefficient ring, which means that we need a ring that has the proper principal roots. And we also need a ring which gives the right result, which means that it needs to be big enough. Okay, and finally, there are a few tricks. One is to twist an FFT entity, which is to transform mod x to the n minus c to mod x n minus 1. And that will give us a simplification. And the important thing is that this avoids gentlemen scent butterflies. And this can be done for radix 3 and higher butterflies. And we can do incomplete entities. And finally, there is a way to do, instead of radix 3 butterflies, we can do what's called the good trick or the good Thomas entity. And this lets you make things repetitive and simpler. All right, and you can combine all the tricks, such as you can do an incomplete good FFT. There are many combinations. So what we did for SMOG-T is the Feynman number transform. And the SMOG-T designers very smartly reused the highly optimized x86 AVX code from Gregor Zeiler, which was used for Sabre in one of my papers. And they are very fast, and it's proven to be correct, and like it's formally verified. But we don't need the modulus that he used, because SMOG-T is smaller, and we can use 3329, 7681, and 10753, and 257. In mode 257, the first triddle is a shift by 4, the next one shift by 2 and 6, the next one shift by 1, 3, 5, and 7. And using smaller modular means no or fewer reductions. And finally, we do twisted entity backwards, which means that we have Curie-Tukey butterflies both ways. The upshot is that we gain about 10% per multiplication, but 23% overall. The reason is that in SMOG-T, we collect many forward Fourier transforms and then do one inverse Fourier transform. So the forward one is faster. So this is why it's 23 overall. And it's currently being verified. So this is the current bench for this level 1. The others are similar. And you can see that it's about 23% total. And for Neon benchmark, they did not provide a assembly, and we have a entity that works pretty well. And this is like on the Raspberry Pi 5. And for Ntrue Plus, the original code was reasonably good. And we find that Koreans are very good programmers, and it took us some work to be faster than they are. And at the moment, we are between about 5% faster. And what we did is that we decomposed it using the good Thomas factorization. And because we can split it into 8 different parts, so we have 32 groups of 8-way like DFT3 operations followed by 3 8-way entities, 32 rows. And this is the current benchmark. And we are still improving and trying to verify all our code. And the ARM Neon code improves a little more, about 15% in every category. Okay, so I think I'm done talking, and I will take any questions.